Hello everyone, my name is Karin Wolff and I'm going to be presenting some of the work from my PhD, which I'm currently doing at UCT. I'm looking at knowledge practices in engineering. This is a profession which, given the exponential and rapid development of technology, has become increasingly complex, as has educating engineers. Now, literature abounds with data on poor throughput and retention, industry dissatisfaction with what practitioners can do from day one, which way the curriculum faces, and for whom. Now, the top complaint in a national survey was about engineering graduate abilities to apply knowledge. That translates as draw on the knowledge you have to solve an engineering problem. Now, the contention in this research is that we have an inadequate understanding of the nature of and relationship between different forms of disciplinary knowledge in 21st century engineering problem-solving practice. So I'm asking the question, how do practitioners apply the different engineering disciplines in a real-world problem in different industrial contexts? And I'm hoping that by understanding how they do this, we'll be able to look back at the curriculum and our teaching and shape it more appropriately for the 21st century. The research theoretically located in the sociology of education, and I'm drawing on two key theorists, Basil Bernstein and Carl Mayton's Legitimation Code Theory work. I'm looking at the relationship between the different core disciplines underpinning multidisciplinary engineering, their different organizing principles, and what this means when they come together in a problem-solving moment. And one of the tools I'm applying to look at this is LCT specialization tool or concept of epistemic relations. I'm primarily interested in the concept of code shifting and code clashes between the different forms of knowledge, between their different organizing principles that emerge when practitioners navigate their way through the different disciplines underpinning their real-world practice. I'm specifically focusing on the multidisciplinary field of mechatronics engineering for two reasons. First of all, it represents the synthesis of very different forms of knowledge. And secondly, it represents those fields beyond engineering where technologies are having a profound impact. Now, the knowledge base in mechatronics engineering is built on three core disciplines: physics, mathematics, and what I'm terming logic. And this term is drawn from the idea of programmable logic controllers, which are used for control systems in the field of mechatronics engineering. Now, the organizing principles behind each of these disciplines, maths, physics, logic, are significantly different. In other words, how the concepts are linked and relate to each other in those disciplines. I've arranged the key elements of a mechatronics curriculum as a Venn diagram to show this kind of different core disciplinary spread. Now, in Bernsteinian terms, here on the right, we have the traditional physics-based engineering regions, mechanical and electrical engineering. Now, it's important to remember that Bernstein's characterization is with reference to the way in which knowledge progresses in the field of production. But it's also reflected in the way we curriculate, the way we teach and learn these concepts. Now, physics, as you know, is what Bernstein terms a hierarchical knowledge structure. We have specific concepts strongly sequenced that absorb lower concepts. Ohm's law is an example, or force. Now, mathematics, which is a discipline applied to all the subregions in this particular knowledge area, or synthesis, is a strong horizontal knowledge structure. That simply means there are different mathematical languages which you could apply to the same phenomenon. Each language has strong concepts or rules that are not necessarily applicable to a different mathematical language. I mean, for example, a linear algebraic equation translated into coordinate geometry. Each of those mathematical languages has its own rules. Now, the third type of structure is a weak horizontal knowledge structure. It's really important that we help people understand that weak does not mean bad. It means choices that are context dependent, like languages themselves, or social science, or information communication technologies. In other words, the phenomenon itself does not dictate the knowledge form, in the way that motion is governed by Newton's laws, for example, or voltage is governed by Ohm's law. Now, I've called this third discipline, for the sake of the focus of the research, logic. Now, these kinds of knowledge are weak in that they borrow concepts and rules across families of the same type, or even families of different types. They're constantly changing. Things become redundant. There's a lot more to be learned here, and you have to constantly be up to date. So the question is, what does this look like when they come together in a problem-solving moment in a specific context? Now, a second theoretical tool I'm using is the LCT specialization concept of epistemic relations. Now, specialization is about what counts, what is recognized as a legitimate practice in a particular knowledge field. Specialization is two sets of relations, those to do with knowledge and those to do with knowers. We're focusing on knowledge, and these are called the epistemic relations. Now, epistemic relations are, and I quote, highlights that practices may be specialized by both what they relate to, the phenomenon in question, and how they so relate. Now, the vertical axis on the epistemic plane is about the phenomenon in question, how strongly it is bounded, kind of by recognizable principles. The horizontal axis is about ways of approaching the phenomenon. The stronger the rules, the stronger the so-called discursive relations. So the left-hand side of the epistemic plane is about more ways, and the lower half of the plane is about weakly bounded phenomena, where you'd have to give a lot more contextual information to explain what you mean. I've translated this plane into a slightly more accessible framework for use with my industry experts. Now, the plane gives us 4 codes, 4 ways of thinking. The top right is purist, recognized principles and associated procedures. The bottom right is recognized methodologies. It doesn't matter what the phenomenon is, it's like following a formula, the structure of an experiment, or applying lean manufacturing rules. Now, this is the doctrinal quadrant. The top left is called situational insight. There are many possibilities for addressing the same phenomenon. Setting up a control system, for example. What I want to control is fixed, but how I do so is variable. Now, the lower left quadrant is where there isn't a strongly bounded phenomenon or any fixed way to do things. This could either be because we are now focused not on knowledge, but on knowers, where other things count, or because there's no legitimate or recognizable practices. Now, each knowledge structure and each of these insights represents a kind of code, a way of thinking, and each code or insight is significantly different. Now, in a multidisciplinary field, it is quite conceivable that one needs to shift one's way of thinking at different times. Now, let's look at how I've used this tool. Very briefly, I had 50 volunteers working as mechatronics technicians or technologists in 3 different types of automation environments. Now, these were classified according to scale and nature of business, and I used Bernstein's classification and framing to determine the different categories. Now, I issued a questionnaire asking for context, the most recent problem faced, and a technical description of how they solved the problem. I then selected 18 of 27 responses I received and conducted a reenactment interview at the site of the problem. This meant they took me through the problem with the actual artifacts. The third phase involved getting their supervisors and my industry experts to verify my analysis. I'm going to show you some examples of how this tool was applied. Now, each case study has a number of features. Now, the model for the case study is based on Herbert Simon's distinction between the inner and outer environments of an artificial phenomenon. Now, in our case, the outer environment consists of a problem solver in a particular problem environment facing a particular problem site. The inner environment of the problem site or artifact is made up of phenomena which constitute the problem structure. And in order to solve the problem solver has to establish a relationship between that inner environment, in other words, the sciences underpinning the problem, and his or her outer environment. Now, I've applied the epistemic relations concept to each of these features to determine a dominant insight orientation. Let's just take a look at the environments themselves. I've taken 4 examples of automation company websites, not of my actual case studies for confidentiality purposes. I've assigned particular insight orientation based on what the company says it values by way of their websites, their personnel, and the actual environment. Now, custom-made design companies usually tell you that their focus is on tailor-made solution for you. In other words, there's a dominant situational insight. Some of the more technically focused traditional companies are clearly purist. Focused is hardcore science and technologies. Then we have a relatively new phenomenon, the ostensibly knower-orientated companies. And then we have those who pride themselves on a particular business methodology, the doctrinal ones. Now, I've applied the same system to the problem solver. One of the sources of data to do this was simply their questionnaires, from their font to the layout to their use of first person. In this example here, we have the literal application of a fixed methodology, 6 Sigma, define, measure, analyze, implement, control. Okay, that's in the doctrinal quadrant. This purist submission in the top right is technically detailed with layers of analytical explanation. Now, the situational practitioner on the top left paints the picture of the actual problem-solving situation with his step-by-step thoughts and action. Right, the problem-solving process itself saw the mapping of the movement from the approach to the problem through the analysis and on to the solution or synthesis. I used an external language of description, here in the table below, to define each of these in the different insight categories. I then literally analyzed their questionnaire and interview texts in relation to these stages. The idea is to get what Carl would call a kind of a soft focus flow, a sense of the overall trajectory. Now, where practitioners had particular problems, in other words, challenging code shifting moments or explicit code clashes, this would actually emerge even in their body language. This example here. This practitioner prefers strong discursive rules. He has systems in place, is strong on his theoretical knowledge. His questionnaire is detailed, very doctrinally sequenced. Now, when he identified the cause of the problem, his entire demeanor changed. He started laughing, almost at a loss. Their international suppliers had changed their design without informing the company. A tiny thing, but which had huge implications and cost the company a great deal. There was a lot of miscommunication, a lot of cross-cultural misunderstanding, and even seeing the scientific cause of the manifestation of the problem was different between the local company and its international suppliers. Now, in this case, neither the company nor the practitioner had measures in place to deal with the different stakeholders or the knowers in this problem situation. So this quadrant here represents a code clash in this context. So pulling all of this together, I'd like to show you one particular case study example. Now, this is what the application of the epistemic relations concept looks like when we apply it to all those features I've just shown you. Here we have a large-scale manufacturing environment, very doctrinal, 6 Sigma business philosophy, lots of official procedures and mechanisms in place. And we have a practitioner who's more of an R&D person. He's a situational purist. Give me the problem, and I'll, underpinned by sound scientific theoretical knowledge, try and solve it. Now, he starts the problem-solving process by explaining the situation. The parts they're manufacturing for a client are being rejected because the barcode on the parts is actually faulty. Now, the problem is that the operators don't insert the barcode sticker roll properly into the printer. The printer then prints the barcodes with chopped off heads. So the operators then edit the content on the actual sticker and bring the text too close close to the barcode. This means the barcode scanner at the client end can't distinguish between text and code, so it rejects the parts. So C2 explains what the people do, what the result of the procedure is, here moving into the doctrinal quadrant, and what the required process should be. And then we have a sudden disjuncture. He jumps into the system he was told to install to solve this problem, a camera system to check that the barcode dimensions are accurate. He does a beautiful technical analysis and explains how this camera system works, and was then integrated to make sure the barcodes were correct. Now he himself identifies the problem as operator training. That's sitting down here. Weak ontic relations, weak discursive relations. But in a company like this, highly regulated, strong discursive relations, they don't have mechanisms to deal with this. So the solution, to my mind, is an artificial recourse to strong discursive and strong ontic relations. Now the longer-term dilemma is that it does not really solve the problem. In fact, it slows down production and leads to all sorts of other problems with the stakeholders, with the actual operators. Now the interesting thing here is that another participant at the same research site has a natural doctrinal orientation, and he's highly effective in this environment. Now this participant, C2, experiences everything in the lower half as a clash, and he actually resigned shortly after the interview and went and joined an R&D firm. So, what does this tell us? There are a few findings to date. Okay, different practitioners have different dominant insights, and different environments require different ways of thinking. All the case studies approach a problem from either a situational or a doctrinal position. These are diametrically opposed, and situational practitioners find a doctrinal environment restrictive, and doctrinal practitioners find a situational environment too open. Now the greatest code clash is along the discursive relations axis, in other words moving between fixed ways and many ways. A few interesting findings that I haven't included in the examples I showed you was that the lower the maths result, I did a full academic profile of these practitioners, the fewer insights demonstrated in the problem-solving trajectory. And high achievers, high academic achievers in both mathematics and logic, which is an absolute anomaly, representing only 2.9% of the 290 students' results I analyzed, those students demonstrate an iterative, diagonal, crisscrossing problem-solving process, showing no problem moving from diametrically kind of opposed insights, easily moving across these insights. Well, thank you very much. I welcome your questions.